All right, we're now live again. Let me just let the people know on the blog here. And I'm just going to put this onto Twitter. Okay. Just going to double check that this is all working. Okay, so just a quick update. Where are we? As always, I'm learning 804. This is Quantum Physics 1. This is MIT's first quantum mechanics class. The prerequisites for it, because a number of people ask me, what are the prerequisites for doing a class like this? So according to MIT, the prerequisites should be 801, 802, 803. So this is 804. So this is the fourth in 8 always signifies physics for MIT. So 8 dot whatever are physics classes. So this means this is the fourth in a series of physics classes, which if you were doing them at the maximum pace at MIT, this would mean that you're probably doing it in your second semester of your second year, sophomore year of MIT, but you could be doing it as a junior as well. So we're not talking about an intro class, definitely. In addition to those physics classes, you should have also taken 1801, 1802, 1803, which are single variable calculus, multivariable calculus, and differential equations. So the 801 is classical mechanics, 802 is electromagnetism, and 803 is waves. So of those 6 prerequisites, the only one that I have never taken is 803 waves. That was not part of the MIT challenge, although I did do 1801, 1802, 1803, 801, 802. So I've done 5 out of the 6. So I'm missing one of the prerequisites, which, as we've been doing problem sets, has been a bit of an issue. Not to mention that the ones that I have taken, I mean, these were courses that I took about 8 years ago. So even though technically I have covered this material, it's rusty. It's something that I'm like, oh, okay, you know, I know roughly what's going on, but I have to refresh it. And that's particularly true of doing the actual mathematical work. So I've been getting my butt kicked by these last problem sets over the last little while. I'm doing problem sets, making pretty basic mistakes. I screwed up 2 times 2 people on the last problem I had. I put 2 times 2 and I wrote down 2 as opposed to 4. So, I mean, some of these errors are pretty trivial. I need to be careful, but it's also a rustiness. If you're not quite familiar with it, it's not in the muscle memory, so to speak, of doing these problems, then you're more likely to make simple mistakes like that because you're trying to keep a lot in your head. In a cognitive science term, working memory is overloaded. You're trying to keep track of too many things, and therefore it's not automatic. And so what I'm going to be trying to do over the next month is build the intuition. So I have an intuitive idea of how you would solve these problems. Build the calculation familiarity. So when I'm solving these calculation problems, they feel more fluent. The answer just rolls out. I don't have to stress over it quite as much. And then hopefully also build some of these atomic components that were learned in previous classes, but maybe need to either be remastered or, in the case of stuff from 803, have to be learned newly altogether. Now, just some notes on the chat. I know some people have been weighing in with questions. I will do my best to occasionally respond to chat things, but I don't anticipate it being prompt. My goal here is to learn quantum mechanics, not just to hang out. So my hope here is that when I have a little bit of a spare moment, I'm not actively focused on a problem. I'm taking a little breather, having a little water, taking a little bit, okay, let's just take a little sigh. I can answer a question or two and then back to work. So I'm not going to try to ignore people, but if I don't answer your question right away, just leave it in the chat. I'll look at it probably later. So right before we get started here, I already have some comments, so I might as well address them right now before we get started with this session. Learning from textbooks versus lectures, basically no difference. I know that sounds really weird because they should be really, one's video, one's text. They serve the same function. The function of textbooks, the function of lectures is there for 2 purposes. 1, it should introduce you to how to do things, so you have a starting point. This is what I call coverage. And 2, it should be there as a fallback when you don't understand something and you have to go back and sort of re-examine what was happening, often with a fine-tooth comb. So I have done MIT classes, about 2/3 of them I just did with notes and textbooks, but 1/3 I had full lecture videos. This class, I have the lecture videos. I like doing the lecture videos. I find them more entertaining than the textbook. Not to mention that they're a little bit easier to do on camera. me reading through a big book with this camera setup. Like, I don't know if you can see it, but my desktop camera here is just like, it's just a few inches above the paper. So I have not as much room to work with as as I would if I were just, if I were reading, I'd probably be sitting back reading like this, but instead I'm kind of reading under this weird camera thing. So I've been doing the textbook though for reference, not to mention I've been using Google and all things like that. Someone's saying if have an expert talk to maybe for an hour a month just to bubble up your incorrect assumptions. So one of the good things about MIT's problem set classes is that your problem sets are, in a certain sense, your expert. They're the ones that give you the test of, do you actually understand this? And then that's how you bubble your incorrect assumptions. If I were doing this class and there were no problem sets, it was just lectures, I would be hard pressed to learn it. I don't know how I would learn it, to be honest with you, because you can watch the lectures and be like, oh yeah, I get that. Then do some problem sets. It's really hard. So there are ways around not having problem sets, but in a technical class like this, they're just not as good. So how do you space the repetition of content? So there's two ways. One is I'm going to call an organic repetition. An organic repetition is just by doing more problem sets, important concepts come up more frequently. And this is a good way to actually do repetition. So if you just do lots of problem sets, just keep doing them. Certain things like complex conjugates, certain atomic pieces, Fourier transform, momentum operators, dimensional analysis. I'm going to get practice on that again and again and again and again throughout this month. So I don't have to worry about spacing really with those. Same thing with recalling concepts. Another thing that you can do is just by keeping an eye on covering all the material and not trying to do everything from 1, everything from 2, everything from 3. What I'm probably going to do is I'm going to do as much as I can, and then I'm going to do as much as I can, and then I'm going to go back and redo some stuff, and then redo some stuff. So I see it as being kind of a spiral where I'm building understanding over the entire material and it's going up, as opposed to just sort of a ramp where you just do 1, 2, 3, 4, 5. I'm kind of circling back, but as I circle back, I've gained information from later in the class. So we're still in the first part of that first spiral, but we'll see how many circles we do. It just really depends on how hard it is. So let me just give you a brief update on where we are, and then I think I'm going to get a little bit more water. I've been quite thirsty as I'm going through this process, probably because I'm talking the whole time. I wasn't talking the whole time doing the MIT challenge. I didn't need to drink as much. Hold on a sec. It's just getting a little warm in the afternoon. I'm going to just drop my sweater off here. So where were we? So where are we in actually processing this class? There's 24 lectures, there's 10 problem sets, there's 2 midterms, and there's a final exam. Now the midterms and the final, I don't know whether I have any solutions for the midterms. So those might be just kind of for fun. They may not actually be a really good evaluation technique. In terms of the lectures, I'm done 1 through 10. Numbers 8 and numbers 9 have some issues I don't understand. So that's probably going to be a good place I'm going to go back to. So of those classes, I would say 8 and 9 were the most difficult and have some issues. They were solving the energy eigenstate time evolution of the Schrodinger equation using differential equations and with this fancy operator method. And both of those methods were quite involved, and they involved a lot of intuitive leaps that I didn't get entirely watching the lectures the first pass. So that's on the lectures end. Problem sets, we are still in problem set number 2, so there's 10 of them. My goal was to get done 5 by the end of this week. Now it's Thursday in the afternoon right now, and I'm only about halfway through problem set 2, so it's not going as fast as I would have hoped. There seems to be a couple of reasons for that. Reason number 1 is that a lot of these early problem sets, so problem set 1 and problem set 2, depend a lot on 803. In particular, the first 2 questions of problem set 2 were like directly drawn from 803, and I've like never covered this material before. So I have to kind of make a judgment call. I'm going to go through all the problem sets, and then the question is, how much do I want to learn that material? Now, if it looks like it's isolated so that I need to understand it for these particular situations only, then I'm probably just going to do a spot learning. So I'm just going to find the lectures that talk about the things that were discussed. So in this case, group and phase velocity, some other things, and go back and do it. If it looks like it's crazy, like it's a really important foundation that I'm missing, I don't suspect that right now. I might do some kind of abbreviated coverage of the entirety of 803. I really don't want to do that because that's also going to be probably about 30 hours of lectures, and it's just going to be messy, I think, to do all of it. But we'll get to that if we have to. If I were really doing this class under normal conditions, that might be what I would do. I just have to go back and do 803. But I do only have a month, so there's going to be probably a trade-off point there. So I'm probably going to do a spot coverage. In addition, there's a lot of stuff that is just, I've covered it, but it's rusty, or I've covered it, but I forget how to do it, or I'm doing the math, but I've forgotten some techniques. And so this is happening quite a bit. And there's really no way around that. I mean, I can go back and learn the concepts, but they're usually the kind of thing that once I learn the answer to the problem, it's like, oh, obviously I should have done that. Well, obviously I should have done that. And so because it's not obvious now, but it's obvious when I look at the answer, it's the knowledge is there. I just haven't been practiced recalling it yet, so it's rusty. So really, this is just something I'm going to push through. I think I'm just going to keep working on the problems. I'm hoping that this is going to just take care of itself so that by the end of the month, I've been doing enough problems so that it's no longer rusty. But it's the same thing as speaking a language, learning any skill. You haven't done it for 8 years, a decade. You're going to be rusty, and there's going to be some discomfort when you're like, oh man, I learned this. How come I can't remember it? But at the same time, the converse of that is that relearning is a lot faster. So if you can push through that discomfort, it's pretty good. And so how do you make the right decisions to not get distracted over such a long period of time? I think one of the big things is having a schedule and sticking to it. Now, for me, when I'm doing this studying, I'm basically doing nothing else. Like, I'm going to interact with the chat a little bit. I'm going to be talking on topic about this, but I'm not going to be playing with my phone. I'm not going to be pulling up messages. I mean, if there's some emergency, maybe someone will message me and I have to deal with something urgent. But for the most part, I'm going to be focused on this. And I know I'm focused for certain chunks of time. The other thing too is that I find this interesting. I find it's something that's motivating to me. And so I think the reason a lot of times people struggle with these problems is that they see doing these problems as something painful. They see learning this material as something that they're not good at, that's frustrating, that, oh, I hate this. And that negative affect makes it a lot harder to study. Now, getting over that negative affect is not something you can do overnight, but I think you can build confidence by working on it more, by training yourself, by building up skill, by having familiarity. Now, for me, I'm kind of bombing pretty hard on a lot of these questions, so it's not that I'm great at it, and that's why I'm feeling it, but it's that I've done this enough. Like when I did the MIT challenge, this was my process every single week for a year. So in some sense, I'm very familiar with at this level of like, I don't know what's going on and I need to fix my misunderstandings. And so I don't feel bad about it too much when I'm making mistakes or I'm getting things wrong. Although being live on camera definitely changes my feelings about that a little bit. So I'm just going to go grab some water. If you have any other questions, now's the time to ask. And then I'm going to try to start right at 2 if I can with going back into problem set 2. Let's try to get problem set 2 done this afternoon. Maybe even a little bit of problem set 3. I'm hoping we can get done all 5 problem sets. I really don't want to have to drag these 5 problem sets out into next week, because I think I'd like to do some Feynman techniques. I'd like to do some drilling down, and it kind of sucks just going a whole week without doing any of that stuff. But I think this is necessary, getting to the first 5 problem sets. Okay, so just gonna get some water and then I'll be back. All right. So do we have any final questions? So one person is saying, did anyone try to persuade you not to do the MIT challenge? In fact, a lot of people told me not to do it. I had a friend who I was considering 2 different opportunities. He told me to go do something. The other one, he thought the MIT challenge wasn't very good. And a number of people I told about doing this project were like, well, yeah, but I don't get it. Like, why study all that? Or I was trying to tell someone, I won't mention his name, but he worked with fairly famous authors. And I remember talking to him because I was sort of excited about doing this project and maybe I could write a book about it and this could be my first book. And I told him about it and he was like, no one's interested in that. That sucks. Don't do that. I did do it anyways, and I'm really happy about that because it's now become my sort of claim to fame, so to speak, as having done this weird project, which I totally wasn't expecting it to be. But yeah, people are always going to say, don't do it, discourage you. I mean, that's just what happens when you're doing weird things that are unique and different. And so that's all you have to do. So internal criticism, yeah. Well, this process right now, I mean, I'm struggling on these and I'm feeling bad about how I'm not able to do a lot of the questions. But the key is to recognize that this ignorance, this failure is part of the learning process. So I'm starting and I suck, and I'm hoping that I'm not going to suck at the end of the month. And that's all learning is. And so never feel bad about doing things badly. Never feel bad about not being good at it, not understanding, not getting it right, because the learning process always starts there. And so if you feel confident in the process, if you know that, you know what, with time, patience, everything just breaks down to atomic parts. Really, like learning, there's nothing magical about it. It's just break the problem into smaller parts, and then you learn the parts and you put together. It's effort, it's work, but it's not magic. So that's what I'm hoping to do in here, is not magic, but just a lot of work, and hopefully you guys can see that. So let's go forward. I'm going to try to do what I was doing earlier, where I have the problem set in a browser window, so that if I have to jump and do calculations or do things like that, I don't have to rejigger my camera setup to do that. I'm going to try to do my my best to make this work. Unfortunately, my microphone kind of sticks up here a little bit, and so I can't see the entire screen. So let's go over. I think this is the view I want. Nope, I'm going to have to pick the screen share again. What are we at here? All right. Okay, so getting back. Let us go back through these problems. So where were we? We were on part 5b, which was talking about delta functions. This is where we left off this morning. So let's read it out. Two expressions, d1x and d2x, involve delta functions are equal if for any smooth function f of x, the integral from negative infinity to positive infinity dx, d1x fx is equal to this d2x. Okay, all right. Let's try to work through some of these problems, see if I understand what that means. X dx is equal to 0. Well, x is equal to 0. X dx is equal to 0 because dx, so d of 0 is the only place that this has positive value, and then at that point x is 0, so it's 0 times d of 0, so it's 0 everywhere. So I don't know if there's a better way of doing that, but yeah. All right, 2. Negative d of x is equal to dx. Well, does this not follow by the same thing here that does this not follow by the same thing that because the delta function is centered around the 0, so if you flip x, it's going to be the same, right? Like it's an odd function. I'm going to say because t of x is odd. I don't really know what constitutes establishing this, because these seem like trivially true to me, but I'll see the notes. Maybe they're doing something fancier to prove this. dc of x is equal to 1 over the magnitude of dx. Okay, interesting. We got to be doing it with these integrals right here, right? So I think I'm going to redo this one with the integrals because I think that's the approach that they're looking for me to prove it. Like otherwise they wouldn't have listed them. So let's try it again. So we have negative infinity, positive infinity, dx. And then we have x dx is equal to we need to put the f of x, I think, for any generic function x is equal to, well, this is just 0 because they're all multiplying each other. No point writing that. So we need to just show that this is 0. So this right here, this integrates to this becomes 1 at x, or so this integrates to 1 only for x equals 0. So x dx. Again, I don't know how to do the math to show this, because when this is, this is 0. I just don't know how to. I don't know how to reduce it more simply because the delta function is like a kind of pathological function. I just think that it's 0. So I'm just going to leave that. Let's see if we do it for this one, if it makes more sense. All right, this one has a non-zero thing, so it's negative dx. So this is going to be equal to f of 0. This is going to be equal to f of 0, which are the same. So therefore, they're the same. Delta cx one over magnitude of c dx f of x. Well, the delta function is defined so that this is at f of 0. Otherwise, 0. I'm not sure what delta cx means. I guess it means if we put 3x there, hold on a second, let me think about this. What would this look like with an example? Like, let's say it was 3. I'm not used to seeing coefficients of the x on a delta x. It's usually like x minus something, right? Because it's in this particular place. It seems weird to scale the delta function. I'm trying to see where the c is going to pop out. Because this only has value at 0. So when that's 0, this coefficient doesn't matter. Well, only thing I can think of where this might matter is this: if the c is complex, and I think that's sort of indicated because c complex like that. Because I mean, if you have like 7 in there, I mean, it's kind of like you put 7x, and it's like you're taking the function that looks like this and turning it into like, you know, this, but it's still the same. Like, I don't understand how that changes it. So we're looking at maybe a complex number. Okay. So what if c were I? So let's just try c equals I. C equals ix. Well, now, but this magnitude means that the complex number is not going to matter, right? Because if it was just I, so it was like 7i. Because you've got to have some kind of, if this is the absolute value of this. This is -1. So I don't think how that's going to change the sign term. Because it's 0, 0, 0, and then 0 is the contribution. I must be missing something like in the limit or something, like if you put a -x. But -x is equal to positive x. So we've already decided this. So we know that sign changes don't matter. So why does this constant change matter? Why does adding a constant scale it? Okay, I'm going to leave this one for right now. I'm just going to put a star next to it. Not convinced of why that is the case. All right, let's try this one. From negative infinity to positive infinity, dx delta a minus x delta x minus b is equal to delta A minus B. So if we know that it's equivalent under a minus sign, it means we can multiply this whole thing by -1. So this is x plus A, x times B minus B. So the integral of these things two multiplied against each other. I feel like I need to know like the limit definition. Otherwise this is not making sense, because this function, you multiply them against each other. You know, if A and B are not identical, these are going to cancel, right? Because one of them is going to be 0 everywhere and one of them is going to be 0 everywhere else. So the delta at, so we can draw this way. So this is minus A, and this is plus B. We've got these deltas right here. Integral of this times this. Again, why is this not 0? Why is it not 0 if A doesn't equal B? Oh, oops, sorry. Jumped ahead here. I'm gonna move my keyboard over a little bit. Why is that not the case? Oh, right, of course, because this is evaluating the function. Right. Okay. So this this only if delta if A equals B, then this is the delta function. If A doesn't equal B, then this is 0. So this is going to be so for each value of, this is dx, for each value of x, we have these two variables. So this is going to be, this is 0 for all A doesn't equal B. So, okay, that is actually my intuition. I was just confused about that. Okay. B, all right, f of x delta x minus A is equal to f of A delta x minus A. Interesting. So I think this is because, okay, so we have f. So f is any function. We have two inputs to it, x and A. So if we take this and multiply it by, take this and multiply it by delta of x minus a. So let's draw this out. This we've got a spike at x minus a. So this is equal to this right here. This is equal to f of x minus a. Oh. But then this is also equal to f of x minus a. Right? It's just because of that's the integral of them. It's not the integral. Taking the integral here. This is a little different because we're multiplying. So this times f of x is whatever the value is here times this. So the value of whatever is here times this. Doesn't seem to me obvious why this would be true. Because, I mean, these could be any arbitrary values. Let's just work it out with an example. Sometimes when you do these problems, it's good to just try an example. And then when you see it's right, maybe you can get an intuition for why it's right. So let's try x equals 3, a equals 10, and f of x is equal to, say, x squared. It's a hypothetical example. So we have f of x, so f of 3, delta of 3 minus 10 is equal to f of 10, delta 3 minus 10. Okay. And this is 3 squared delta of minus 7, which is 0, equals 10 squared delta of 7, which is 0. So if x doesn't equal a, delta of x minus a is 0. So it doesn't matter that they're different. So x must equal a. I think that's the trick. These delta functions are sneaky like that. All right, let's go through part B then in the solutions. And I think there was the one that I didn't get. Let's try that one more because I think maybe I'm missing something obvious again here. Let's work through an example. So the integral of this, let's just try 7, plugging 7 in. So d7 x f of x dx. So this is the contribution of this is 0 when this is 0, but when it's 0 here, it's equal to f of 0. And what's that on the other side here? Is equal to so this is also zero everywhere except for f of 0. So this is going to be right here is going to be I don't know why this should be 1, right? This shouldn't be 1, rather this should be f of 0, right? And then this is f of 0 divided by the absolute magnitude of c. So that's not clear to me why that scale factor is impacting it. Right, so this is the one that I don't understand. So let's go through and see what the answers are. Problem 5, delta function. So we did A, B, 0 f of 0 equals 0, C, okay, equals f of 0 equals this, okay. Assume C is greater than 0, then okay. All right, let's just show this here. So I'm going to switch to pen so that I can mark down what their results are. So assume C is greater than 0, then let U be defined as Cx. So let U to be defined as Cx. Then if we take this integral, from negative infinity to positive infinity of, what's going on here? You know what? I'm going to break this out on a new page. Right here. Sorry, I need space. No, let's do it here. We need positive infinity delta Cx fx dx minus negative infinity positive infinity delta u f u divided by c. Oh my god. Du c 1 over c f 0 why are these all minus? Minus x c fx dx. Okay, wow. This is something I'm not quite understanding. Let's look at this. I think this must have been it is an equal sign. It didn't draw it properly. I was like, what is going on here? Okay. Why is the DUC happening? Okay. It's because we've changed So instead of dx, so all right, so this dx is getting turned into this. Okay. Because when we scale, all right. Yeah, okay, so let me write it down. This was something subtle, and this is basic calculus, but it's been a long time since I've done this. So this gets shrunk because the x factor when turned into du must also be scaled. It is only the magnitude because when du is negative, the all right, let's look at this point here. Why is it only, so if c is less than 0, then we have, we'll pull out a minus sign, equal to minus this. The limits of integration get swapped during the substitution. Okay, this part here I think I understand, but I need to be careful about it because often I'm just forgetting about dx, and I'm just treating dx as just sort of part and parcel of this whole integral thing, but it's doing something important, and in this case, that was the key to solving that problem, is recognizing that that is also a quantity, even if it's an infinitesimal. All right, let's go back over to the problems. We're now on C. C. It's a little dark here. I'm just going to open these blinds a little bit. Get a little bit more light in. I'm having the sun go kind of over and atop me, so it's changing the light throughout the day. Show that the following are valid representations of dx. Part G, dx equals dx is equal to 1 over 2 pi negative of infinity to positive infinity dk e to the I kx. So, well, when we integrate over a complex integral, we get 1. And so if x is anything other than, I think we got to just, to do this mathematically, we got to display this as another integral. So let's go back and do the other integral. So in order for this to be valid, we have to be this time we're integrating over over dx, and this time is dk dikx, and then this is f of x. So if we multiply this by f of x, we should get it. This should be, hold on a sec. What do I want to do here? This is supposed to be take the integral when x is going to be for all x. How do we get this here? We show, basically we have to show that this is 1 when x is 0. Sorry, not x is, yeah, x is 0. Hold on a sec. Let me erase this right here. But we know this is true just because this is the flip between momentum space and position space for quantum mechanics. But how do I show this? Integrate over this, you're going to get 2 pi. So that's why we got this factor of 2 pi. The fact that the integrals are the complex exponentials are an orthonormal basis, I think is key to this here, because if you were to form, basically you can't form this with any contribution other than other than itself, right? Delta function is going to be 0 for x doesn't equal 0. Infinity for that. So if x equals 1, or sorry, if x equals 0, this whole thing equals 1 from 0 to infinity. But how do I show that if it's not 0, it's 0? All right, I'm just going to spell it out intuitively because I'm not quite sure how to do the math, but essentially what we're looking at here is if x is equal to 0, then this is just a constant function at 1, right? And so if we were to, this adds up to infinity, obviously. This is just a constant function at 1, is it, or is it 2 pi? No. 1? And then if x doesn't equal 0, well, then we've got a sinusoidal, right? And this, the unbounded integral of this should be 0, right? Because there's as much contribution from the top as there is from the bottom. I'm trying to think of how to get around the whole infinities here when I'm calculating this. And where's the 2 pi coming out of? Okay, this is why intuitively I feel like this makes sense, but I'm not quite sure how to show it with the math. For all values of k. So all frequencies of k. All right, let's leave another star in this one. Come back to it. See if I can have any more luck with 2, and then we'll get some feedback. All right, 2. X equals limit alpha goes to 0. And dA this dAx equals 1 over a root pi e to the negative x squared, or a squared. So this is what the other person was talking about one representation of the delta being this Gaussian of infinitely narrow width. This is Gaussian. Again, showing this is going to be tricky. So let's see if I can show it. All right. Well, as a goes towards 0, then so let's just do it with capital A. So this is going to be a. So let's say a is very small. So this goes to infinity, and e to the negative x squared, a squared also goes to infinity. So it is kind of like a Gaussian that is getting taller and skinnier until it gets to some point. If anyone wants to do this, you can see here I've got 804 spring 2013 problem set 2. So if you Google the MIT 804 spring 2013, you'll get to all this material. So all right, I've got to use this integral here and how it's, the integral is the key to showing this this works. Oh, part G. All right, this is the last question for this problem. So I don't have more than this. I'm running problem set 6. We've got to take the integral here. See, my question is, I'm not sure why this factor drops out of root pi. Assuming it's because this is squared up here. So if we're squared, we're dropping a factor of if we were to well, this is a lot harder than the last one. So we want to see that the behavior of this matches the behavior of the function. And so the behavior of the function is such that from positive infinity, negative infinity, dx, this mess here, 1 over a root pi e to the negative x squared over a squared times f of x we want this to be equal to f of 0, no? Do I need to have those ABs there? I don't know whether I need to have those ABs there. To f of 0. Let's just check for a second what the let's just look what the integral of the Gaussian is. All right, well, we know from this, so our crib sheet is that it's root pi. So the integral of this from here is root pi. Now, if we have some factor, do we have some factor we can scale this by? All right, it's this is okay. So because of this Gaussian integral, we know that so that's where the root pi is coming, is because this is the integral of the Gaussian. So this a is dropping out. 1 over a here must be because of the same reason that this is a scale factor, right? So if this is 1, do we have anything? Do we have any formulas that look like that? Well, I have a over here times this squared. So if a is squared, so then this would be, if this is a squared, then it's going to be, if this is root a, then it's going to be a over here. So I'll just write it this way. Because dx e to the negative x squared is equal to root pi, then, oh, sorry, let's change this to the one they have there. Is negative ax squared is equal to root pi over a. Root pi over a. Therefore, dx e to the negative a squared, sorry, x over a squared, x squared over a squared is going to be equal to root pi divided by a. So if we have, right, root pi over a, how do we get the a on the same side here? So the root pi's cancel. The question is, the a drops down because it's 1 over here. A squared. Over a. Oh, no. Sorry, this is because this is 1 over a. This is a root pi over here. So therefore, with this right here, when we have this factor, it's going to cancel in the integral. So this is going to be equal to 1 which is going to be times this. It's going to be 1 times f of x. Now, when this limit, when a gets very large, this is the delta function. So how do we handle the limit here? So we know that the constants are right. This factor makes sense because of the Gaussian integral. But let's look at how this limit's working. Now, as this gets very close to 0, when x is anything other than well, this right here is going to be negative ax squared. This is going to be increasingly large. It's also going to be increasingly narrow. How do I handle the derivative as this goes to 0? How do I handle the integration as this goes towards 0? This thing is controlling the height, and this thing is controlling the width. So as this gets smaller and smaller, this gets narrower and narrower, and this gets higher and higher. But the contributions cancel out. Yeah, I don't know another way of showing this. What do we have for the other one here? So, all right, I'm going to go check the answers because I have an intuition of why, but my math is not as shaking. I think this is because I may be forgetting some things from calculus where I could actually rigorously show this rather than having like an intuitive idea about it. So let's look at the answers right now. So C. Did I miss something here? Oh, we didn't look at 1D, so did I get these right? This one here. Fx okay, that's not how I did it, but I think that my approach is still valid. What was V? V was this and V times G of X dx FAG equals sure. All right, now let's go to C. Fy d to the xy dy minus is equal to f of x. Okay, let's read through this. Consider the inverse Fourier transform. Okay, now suppose we substitute into this formula for the Fourier transform, that is f tilde k, this. Result is All right, I'm gonna need to write this down because a lot of this is tripping me up. All right. Consider the inverse formula. Consider the inverse Fourier transform equation. F of x equals 1 over root 2 pi I k of f tilde dx. Now suppose we substitute into this formula the Fourier transform. Okay, that's the inverse Fourier transform. The result is this, so let's write this down. F of x equal to negative infinity, positive infinity, e to the I kx, all in brackets, 1 over 2 pi, negative infinity, positive infinity, e to the negative I kx, fy dy dk. From x to y. So we had to rename this to y. So this is important because we're differentiating twice now. Changing the order of integration. What do we have now? dk dy. So how did we do that swap? Let's look it up. This is something that I don't remember. All right, I'm not going to watch a YouTube thing just because I don't want to. All right. Examples of changing the order of integration in double integrals. Given a double integral, this, of a function fxy over region D, you may be able to write it as two different iterated integrals. You can integrate it with respect to x first or integrate it with respect to y first. If you integrate it with respect to x first, you will obtain an integral that looks something like this. If you integrate it with respect to y first, you'll obtain that. We often say that the first integral is in dx dy order, then this is dy dx order. So let me go to my textbook here from the previous class. So where is my calculus textbook? Calculus. You can tell I haven't opened it in a while because of how long I'm taking to find the book. Where is it on the shelf here? I've got elementary differential equations. Multivariable calculus. Do I have single variable calculus, or is this the same book? I think this is going to be a multivariable calculus. So this was Edwards and Penny, 6th edition. Again, I use this for the MIT challenge. Let's see if I can find changing order. No, this is just a change of variables. I'm going to change the order of integration. And I'm going to put this back because I'm not sure whether I'm going to be able to find it very quickly here. Might be just easier to work off of an online resource. So let's go back to OpenCourseWare, nice. Should be Creative Commons. All right, guys, we're gonna watch another video. Oh.
Hello, and welcome back to our citation. So the problem I'd like to work with you today is this one here. It's just to compute this two-variable integral. And the integrand that we're going to be computing is e to the u over u. And what you might notice right away is that this inner integral, it's an integral over u of e to the u over u. And this is not an integral that we have a nice formula for from one variable calculus. So I'm going to suggest that as you try to solve this, you think about how can you use the fact that this is a multivariable integral, maybe doing swapping the order of integration, etc., to solve this. So why don't you go ahead and work this problem on your own, check back with me in a few minutes, and I'll see how I did it. So I've drawn the t and u axes here. And now let's look at the region of integration. So t is running from 0 to 1/4. So we'll just draw 1/4 about there. And now the range for u, the bottom range is the square root of t. So we're going to draw the curve u as the square root of t. Just looks like a parabola on its side. And then the top bound is at u equals 1/2. And notice that that when t is 1/4, that means that u is 1/2 because u is just the square root of t. And so what we're really interested in is this region here, the region between the square root of t, u is the square root of t, and between u is 1/2. So this is our region. So let's see. Let's rewrite the integral to be by swapping the order of integration. So I'll do that here. So now we want to put on the outside. We want to put the range of u first. So the range of u, we can see on the graph here, u ranges from 0 to 1/2. So that's going to be easy. And now t, so t is always starting right here at t equals 0. And it's always ending at this curve, which is t equals u squared. So we have these little intervals here. And so our ranges for t is going to be t is running from 0 to u squared. And then we have the same integrand, e to the u over u. Now we have dt du. All right. And now we see that this was a nice thing to do because look, the first integral that we need to take is an integral in t, but our integrand doesn't involve the variable t. So this is going to be a very easy integral to take. So I just take that integrand and I just multiply it by the constant t. So we just have e to the u over u times t. And then it's a definite integral, which ranges from u squared to 0 du. And so this is just going to be 1/2 here. this is really just going to be u e to the u du. All right. So now, so let me write that up over here again. So.
Okay, so let's go back to this problem here and see what the heck they did here, because they changed the order of integration. So this is, we're doing a double integral problem. And so our original format is we've got y and k. So let's, you know what I'm going to do? Go back to pencil because this is my work, as opposed to copying down some. So we're doing y and k. So in this one here, we're first integrating e to the negative I kx over fy times fy dy. And then we're taking this from negative infinity to infinity, and we're taking the other integral, or multiplying that, taking that integral times e to the I kx. So this is a little trickier because they're not just next to each other. These integrands are not just next to each other. There's terms in between. So this is a constant. So I mean, this 1 over 2 pi is a constant. So it should just pop right out. So let me look again at what we have for the solution here. So how are we converting from one to the other here? E to the I k is 1 pi fy dy infinity. And where does our f function is any generic function? I think f of x is equal to how do we get to the end of this? Let's just see where the ending result is. Dx minus y. Oh boy, all right. How did they execute that change in the order of integration? Which question is this one? This is 5. Did we have a problem doing 3? We're integrating over this, and we need to change how we're integrating it. And it's e to the I kx. And then we're doing e to the a. How do they execute this changing the order of integration? Yeah, I don't know. All right, I'm going to just put a little note in here because I think this is something worth going back to. Okay, and let's go on to question 2, which we had some stuff, but we didn't get that much luck with it. So let's look at question 2. We want to show that this limit, so this is, let's do it. Okay, so let's just write down here. So we want to show that negative f of x limit as a goes to 0. A root pi e to the negative x squared over a squared dx is equal to f of 0. This is what we're trying to show. First, take the limit outside the integral. So we can just bump this over here. I think I have this here, yeah. Then we have, I did write this part. So far, so good. All right. We now non-dimensionalize by letting u equal xa. Okay. Change of variables here. So we have limit a goes to 0. FUA 1 over root pi e to the negative u squared du. Okay, yeah, that makes sense. The only remaining factor of a resides in FUA, so we can technically take the limit and say as, so FUA goes to F0, which then comes out of the integral because it is now a constant. So this comes out. I'm running out of space here. Limit. Recognize that the integral is a standard Gaussian integral that evaluates to 1. We have thus shown that this is true. Okay, so the main thing that changed here is we used a change of variables to get it inside of f. Now, when the limit was applied to it, we know that that becomes 0. So this is going to become 0 regardless of what a is. It just becomes a constant. It's no longer part of the integral. And f of 0, and then this whole thing just turns into 1. Okay, that one makes sense. The other one, I'm not entirely sure what they did there. So this one at least makes sense. I am missing some techniques, but I at least understand the solution. So let's go back over to problem set. Where are we now? Okay, we're now on question 6. Question 6. Qualitative structure of waveforms. In lecture this week, we looked at a number of example wave functions, sketched their Fourier transforms, and estimated our confidence in predictions for measurements of the position and momentum of the corresponding systems. In this problem, you will make those arguments precise by explicitly computing everything we discussed. Consider the following non-normalizable wave functions for a particle in one dimension with x a dimensionless variable. Hold on a sec. Oh, this is okay. For each of these wave functions, sketch the wave function and the corresponding probability distribution. Plot the real part only, okay. Find yourself sketching a delta function or its square. You may replace the delta with a narrow Gaussian as you justified in the problem. Okay. So, so this size x is equal to approximately x equals -1. So let's go real psi 1. And then let's plot it out. So this is x minus 1. So we've got 0. This is 1. And then we've got this here. And the probability psi 1 is going to be similarly over 1. All right. So just put this forward here. And then the integral of this is also equal to 1, but I guess I can't really draw that. All right, let's do real part of psi 2. And it's x minus 2. All right, though this is 1, 2. And similarly, 0, 2. That should be clear. Norm squared. All right, those ones are pretty easy, I think. Let's do, I'll just write these notes so that I can have it clear here. Psi 1, psi 2. What are the other ones? Compute the Fourier transform. Sketch this and the corresponding probability of, where's the part? Okay, so I'll just do everything all at once here then. So I'm going to do real psi tilde 1. Probability psi tilde 1. Real psi tilde 2. Probability psi tilde 2. So this is going to be I think what we're going to see here is this going to have this should be flat, no? I don't know what the height is. Once again, this is going to be, I think it's not normalizable, but we should say delta x very small, delta p very high, and similar, and this is also delta x small, delta p high. Oh, where's the particle most likely to be found? So a high probability at 1, high, oops. Oh, wow. Terrible erasers. High probability at 2, and I'm going to say NEP. NEP. All right, let's go over to the next ones. Try to spread it out a little bit more. I got a lot to write there, so let's do psi 3 is going to be e to the I k. So that is e to the I k is the real part is the cosine. So real, let's just do like that. And probability psi 3 is just a constant. And then we have real psi tilde 3 at ix. So this is at k equals 1. Goes up. And probability psi 3, update k, put x here. This is going to be 1. Very high. And so this is going to be delta x high, delta p low, anywhere momentum is equal to what? H p was equal to hk? No? So equals very close to h. Is it h or h bar? Eesh, I should memorize this. H bar k. All right, now let's do psi 4, real psi 4. Okay, so it's 2, so we've got a narrower one. Probability psi 4x. Now we have real psi 4 Fourier transform. We'll do 0, 1, 2. And this one is 0, 1, 2. This is probability psi 4 of k. X is high, frequency is low anywhere, and this is 2H. All right, and then we have psi 5. Psi 5 is these two. Okay. Real psi 5. It's at -1 and -2. Probability psi 5. And then let's go real psi 5. This. Oh boy, all right. So this is going to be two sine waves. So let's just sketch out an envelope here. Maybe make it a bit smaller. And then we need one twice the frequency. So we have oh man. Oh, it's hard to draw sine waves and make them match up and not screw this up. Okay, so there's going to be a maximum at 2. It's going to hit 0 at 1/2 pi. And it's going to hit -1 where this hits 0. Where this hits 0. And then it's going to go back up here. And it's going to hit positive again here. It's going to hit up here and hit positive again here. So we need to sum these waves. So it's going to be what? This. I think. Then here we have this going up and this going down. Do we go up again or do we go? And this goes up high. This is down low. Oh, do I have a better eraser? I think this eraser is better. Oh, how drawing these things is annoying. So it will be I think it's going to be like this. that. I think that's the rough shape. Oh, one jump up. Is it 2 bumps or one jump up? Bump up, bump down. Oof. Let's just plot this on Wolfram Alpha quickly, because I'm bored of drawing. Let's do Wolfram Alpha. All right, I want cosine of x, cosine 2x. Sine 2x. So it should be and this is cosine squared. So this should be just sharper, I believe. Oh my gosh, this is so ugly. All right, so we know that delta x, well, it's going to be, what is the exact question? Is it xing for delta x, or is it just, all right, so we know that x, this is going to be most likely to be found. Well, I mean, it's 50% at 1 and 50% at 2, so this isn't really this. And then delta x, I mean, I don't really want to calculate that right now, but low, I mean, there's not 0, but it's low. And here, momentum is high, not everywhere constant. And all right, psi 6. Real 6. Which one's psi 6? E plus this does this. Okay, so we're doing the opposite now. So this is real, and then probability of x, psi 6. 0. So it's like oh my God, this is so hard to draw. All right. And we have large, not infinite, and we have delta P. We have P is either 50%, K equals 1, 50%, K equals 2. Where are we next? Size 7. Okay, so now we've got real. I'm just going to write real probability. Okay. Probability is like this. Okay. Uniform P density. Let's put X for position. Momentum. The momentum is now going to be the Fourier transform of this. It's going to have contributions from the whole thing. I don't know what the Fourier transform of this square potential looks like. Ooh, it's probably this. It's probably number 8. So it's something like this. Something like that. Oh my God, I can't draw this. All right, and then 8. That's just the reverse. I'm not going to write all that down. All right. For x8 only, determine the normalization constant n up to an overall phase. All right. Normalization constant n up to a constant phase. So what do we know about this? Well, we know that it's going to be a over root pi. Right? I mean, this other thing doesn't need to be normalized. And F. Calculate the expectation values XP and the uncertainties in this state. Yeesh. Well, we know that this is going to be x is equal to 0. Or no, sorry, x is because it's minus x naught. So it's going to be The expectation value is going to be x naught because it's centered around x naught. Hold on a sec. Let's center this around x naught. All right. No, is it not that? This. Oh, what's the standard deviation of Gaussian? So standard deviation of Gaussian is this underneath term. I've already got the root pi. So it's going to be what? 1 over root a? Yeesh, this is a bit of a guess. Two over root a? There's supposed to be a 2 there, right? Root 2 over root a? I'm guessing because it's going to be this. And P is just how do you find the variance of a box like that? It's going to be the integral from minus a divided by 2 to a divided by 2 of what? This value squared. Pi a squared over pi a squared. Like basically we got to just get the difference here. That's what we're calculating. A squared x minus so minus the average is just x. pi. Pi squared. So this is going to be, I'm going to just check to see whether I'm in the right. Oh, that's like G. This is FG. What happens to the shape of the wave function as a goes to 0? Happens to this. As a goes to 0, our momentum is shrinking, but our position is going up. Yeah, let's just see what the answer is. Okay. I'm just going to go through one of these. All right. All right. All right. All right. Right. All right. Yes. I think this is right. I'm just going with a much higher K naught. So I think this is right. All right. Yeah, again. Oh, oops. Oops, I made a mistake there. Yeah, this is right. This is right. Again, same thing. A7. Yeah, I mean, I think this is also right. Yeah. Maxima, Silent. X1. Two. This one here is yeah, same thing. Is it H? Yeah, H bar, yeah. Particle will either be at x equals 1 or x equals 2 with equal probability. Yeah. Most likely 2n pi h bar, where n is any integer. Okay, so I did not put the exact answer. This is 2n pi h bar. And particle 6. Same thing. Oh, k equals 1, so I should say, yeah, h bar or 2h bar. Particle mostly be found at 2n pi. All right, yes, okay. Most likely be 0. Well, yeah, okay. Okay, same thing. N equals I have. Yeesh. Ooh. Of course. I'm taking the, we're gonna do norm squared of this. All right, yeah. Okay, so this. So to be properly normalized, this answer is equal to 2 over pi a squared power 1/4. N squared a pi by 2. Pi by 2. Oh, it's pi by 2. Thought it was root pi. Oh, there's a 2 there. Why is there a 2 there? Let's go look at the question again. Yeah, why is there a 2 there? think we have a 2 here. But here we don't have a 2, do we? No. So why is there 2 there? I got to say, the fact that on Chrome some of these latex symbols are not showing up is super annoying until I highlight them. Did we get? Oh, of course, because it's norm squared. So we're adding an extra factor of 2. Okay, that's why. It's norm squared. Okay. All right. That's just because I did it with squared. All right. Now let's go forward. F. Using symmetry. It's not. Okay, so we got that right. Uncertainties are given by this. Oh, wow, they went through and computed everything. So x is equal to a by 2. I think. Yeah. Okay. All right. All right. G, the position space waveform psi 8x gets narrow and taller as a goes to 0. We thus expect x, variance in x, standard deviation of x, uncertainty in x, that's the way to say that, to tend towards 0 as this happens, which is confirmed by what we found in part F, which is this is proportional to a. Conversely, the momentum space gets broader and flatter, and infinity is again confirmed by 1 over a. Oh, do we have another question? Yes, problem 7. 7, 8. Okay, can we try to get done 7 and 8 today? Problem 7. Why the wave function should be continuous. Consider the wave function. This from problem 6 was just a step function centered on the origin. On first glance, this looks like a perfectly reasonable wave function. It's normalizable. X is finite. Its Fourier transform is simple. However, it has discontinuities here acting on it with this leads to divergencies, in particular divergent expectation value for the momentum. To make this precise, determine the normalization constant n and calculate the uncertainty this. How does that compare with your estimate from problem 6? Okay, we need to determine n of so the integral from negative infinity to positive infinity of it's just a constant, so it's just n. I don't think I even need to integrate this. This is dumb. We know that this area is equal to 1. Yeah. Squared, whatever. Then therefore this is with a, and n is equal to 1 over a. And this is equal to, well, now we're trying to figure out what's the uncertainty in this. So expectation of x squared is going to be equal to a squared. Expectation squared of the squared is equal to, we have to square this for each of them. So this is 0. Which is equal to what? So we had, now this is now turned into a square, right? So it's going to be equal to from negative a divided by 2 to a divided by 2. We now have whatever x is squared, x squared dx is equal to, so this is 1/2, no, x. I'm going to get the squared here. Right, x squaring each value. Oh, brain's getting fuzzy here. I am now messing up basic stuff. All right. And just take a little pause. Think about this for a second. And just turn to something else, and then I'm going to go back to it. So we have a few people who are watching, I think. I'm not sure whether my chat here shows anything. So a few questions from the comments. Do we have anything here? So one of the questions was from Jail, I think. I'm not sure how to say your name. Scott, if you wanted to prioritize knowledge over intuition, you get feedback for your answers instantly. So I think it's important to talk about feedback in two ways. So when I commit to a response, then I should get feedback right away. So meaning that I can look at the other answers. So I haven't been going back and forth between questions immediately because in some cases it's not particularly necessary. But I would consider feedback to be immediate if you're getting feedback on stuff that you've covered so recently that you easily remember the full response that you did. So doing feedback a day later is not usually as good because you have to familiarize yourself with, well, what was the feedback? You got to reactivate all that knowledge to understand what you were even doing to correct your response. So, I mean, getting feedback after I've done a couple questions intervening is not usually a big deal. But I want to compare that to getting feedback like, oh, I don't have the answer, let's get feedback right away, versus let's struggle it out on the problem for a while and then get feedback. And in general, I think particularly with these kind of hard problems, I recommend doing a bit of struggling. Struggling out is good because for two reasons. One, when you get the feedback, you're going to pay attention to it more. If I don't spend any time thinking about it, then I'm kind of like, to use our mathematical analogy, feedback when you put in very little effort and then just go check the problem immediately. This almost in the limit is essentially just looking at the solutions without even doing the work. So the gap between the amount of work you put in before checking the solutions is essentially, this is where the learning is happening, or this is where you're developing that response. Now, struggling on a problem and going down the wrong road and getting the question wrong, and this is not necessarily ideal either. So I tend to have kind of a trade-off point where I put in some effort to try to figure it out, and then I get feedback. Now, I think if you have more problem sets, it's easier to get more feedback. I don't think I have solutions to too many problem sets, so I'm pushing a bit harder on these ones for the same reason that once I run out of problem sets with solutions, it's going to be a lot harder to get good practice because I am not going to be able to get feedback once I'm actually really trying to solve the problems. So in general, that's how I look at it. Now let's go back to this problem that I was doing earlier and see if I can't look at it with fresher eyes. So we were trying to get the expectation of this x squared, which I'm taking the integral of this, but every value is squared. So this was the constant function. So it was x equals a at all points in time. And here it is a squared for each value. So this should be a squared. No, what am I doing here? Why am I not able to integrate this properly? Because I want it to be integrated from here to here. And it's the value is equal to this is not right. Expected value of x is 0. So this squared is also 0. This right here is going to be, well, we know what the normalization constant is 1 over a. And the value is squared, no? So we're squaring every single point. Yeesh. All right. So if we we evaluate this, I might be totally over 8. equal to, what is it equal to? It is equal to what? It is equal to a squared divided by 8. Is it 1/8 a squared? All right, let's check the uncertainty. Ooh. 12. What? And he was 1 over root a. First, we find n. Oh, yeah. I'm forgetting these. Oh, I'm already with the pen. I'm forgetting these because I was supposed to do it with that. So I've got to remember there's a factor of square whenever we're going from. I'll write that down. Need to remember. Okay, so that's 1 over root a. This is 1 over root a. We know we need to find x squared, so x squared is equal to 1 over a x squared dx. So let's just check this again. So we were on the right approach. 1 over a negative 8.5 x squared dx is equal to 1 over 2a x squared dx. We've got that at, this is a cubed and this is x. This is 8.5. E cubed 8. To a. Why isn't this 16? Why am I getting 12 here? What kind of basic mistake am I making to get 12? Because do we just have 1 over a 2a? Sorry, 1/2 a cubed 8. Why isn't this 16? am I not? Can you guys not see my answers here? So the question is, why is this 12? Because I'm making a simple mistake here. Because we're integrating. X cubed, drop the 2. No. Okay, so when we differentiate this, we drop down a 3. So this must be a 3 here. We drop down a 3, we get, so it's x cubed. This is equal to 3x squared. So we get 1/3 x cubed. So this is, yeah, this is a 3. No, that's 27. That's too high. Oh boy. Yeah, I'll push this up here. So we get these multiplied. There's got to be a factor 2 somewhere. Where's the factor of 2? Oh, Jesus. Wow. So this is 1 over 24. Sorry. A cubed over 24 plus. We cancel this. Drop down a power. And we have 2 of these. So this becomes 12 equals 1/12 a squared. Wow. Okay. All right. Sometimes it takes a while, guys. All right. Let's go over here. How does this compare to the estimate from problem 6? Did I have an estimate from problem 6? Oh, I need to do that. That was only half of the work. Oh, no, but it's, hold on a sec. So it's 1 over root 12 a is equal to delta x. No? Let's check. 2 root 3. Yeah. That's the same thing. Okay, that's the same. All right. We got that little part right. So thus the spread of delta x is thus smaller than the value we found for than the previous problem. How did we find it in the previous problem? Yeah, I must have missed that. Okay. Part B. And using the Fourier transform you calculated in problem 6 and your results from problem 4. Oh boy. Alternatively compute provide. Verifying this gives the same divergence as straightforward, but involves delicate manipulations involving derivatives of delta So Fourier transform. Fourier transform. It's going to be e to the ikx 1 over root 2 pi normalization e to the ikx f of x. Am I not forgetting a minus sign? Let me double check. Fourier. Where art thou, Fourier? Okay, yeah, I'm forgetting a minus sign. Wait, where are we? By using the Fourier transform. Calculated problem 6 and your results from problem 4. Did we calculate the Fourier transform? I don't know whether I did. So we have f of x is equal to n0 I'm not sure how I'm supposed to calculate this Fourier transform. mean, maybe we can just go directly from this. Like, this is the Fourier transform. I don't know what it's going to boil down to. I think it boils down to this thing, no? But how do we get that? Oh. Right. Because it doesn't exist out of this, so that's the key. So let me do this with the pen. So we can change this to n over root 2 pi negative a divided 2. It's the bounds. That's what we're changing here. Negative kx. So this is equal to the Fourier transform, and so we need to figure out what the bounds are. So we have the ikx is going to be what? Derivative of this is negative. So it's 1 over ik e to the negative ikx evaluated at a half and a minus 1/2. It's going to be, I'm going to switch over to pencil again. Just if anyone's wondering, I'm trying to do things that I get help with pen and my work in pencil so that I have a better sense of, if I look through a bunch of answers and it's all in pen, I can tell that I needed a lot of help. Whereas if it's all in pencil, I know that I mostly did it myself. It's a good thing for remembering later if you need to figure out, you were doing a lot of like kind of going back and forth between them learning processes, and you don't want to convince yourself you understood everything when really you were mostly copying stuff. So we have n over root 2 pi, and then this is going to be over ik. We can just change this to negative ik. Negative ik, and then this is going to be plus ik. And then this is going to be our a half term, e to the negative ik a divided by 2 e to the ik a divided by 2. So we know we can just flip these around. So if it's if it is the ik minus, is this sine or cosine? How do I know it's sine or cosine? So we have e to the, just from trigonometry, e to the I kx minus I I might be missing something here. Let's expand it out before we substitute, and then I can make sure I get my identities right. Okay. So we have, instead of this, we're going to be having no, I don't want to do sine. This is complex exponential. I don't want to do the integral otherwise. Equals, and then this is e to the I x is equal to cosine plus I sine x. This is equal to cosine x minus I sine x or plus I sine x. Let's double check that. Euler's formula plus. So this is plus. So e to the negative ix is going to be what? E to the negative ix is I think it's just minus, right? No, it's rotating. That would be cosine minus x plus I sine minus x. Cosine is equal to minus x. This should be the same. And this is equal to minus, right? That's right, you know? Signs, odd signs, even, so this should be equal to what? Cosine of ik a over 2 minus I sine ik a over 2 plus ik and then this one's the opposite. This one is cosine of cosine of, oh, no, not I. Oops. Of k over 2 minus, plus sine ka over 2. Eesh. Okay, now let's go back over here. We have n over root 2 pi. Still got 20 minutes, good. All right. And then what do we have here? Well, the cosines cancel. And then, oh, oops, I here. And this becomes a plus. Oops, I gotta be less careful. I'm more careful. This cancels. This cancels with this. And we get left with minus hold on. I'm going too fast. All right. Cosine Ka over 2 cosine Ka over 2. This is what? This is Ik cosine plus Ik cosine. So get rid of the cosine terms. We have negative I k times I is going to be equal to 1. So this is K sine Ka over 2. And then this is I just negative 1. No. How am I deleting all of my signs? Oh boy. What did I do here? I must have dropped a sign. Because I times I is equal to negative this, and then we get rid of it. Get rid of it. Or did I make a mistake with I kind of cancel? Yeah, there's definitely something wrong here. Oh. This is negative. They're both negative. So we have negative 2k. Negative 2k sine. Which is all right. This is our so I think this right here, because of this k here, this is going to keep getting bigger and bigger, right? So that's why it's divergent. Let's check if that's right. This sine k over k. Over k. How did I move the k down? How did I move the k up? Yeah, the k is over here. How did I move it? Why did I do that down here? Multiply by negative I. Yeah. over k over k over k over k. Root 2 and then 2 divided by root 2, we can bring the root 2 up. Root 2 over pi. Yeah, okay. So otherwise my thing is right here because we have 2, oops, 2 up here. By symmetry, this equals 0, p squared we have. Oh boy, all right, so this was hard, but I do think that I got the understanding of the problem there. And now let's go on to number 8. Ten more minutes. I'm gonna just push through on 8. Oh, let's use the pencil here. I'm gonna just push through on 8 right now. See if we can, 10 minutes is probably not gonna be enough time. All right, as you've shown, discontinuous wave function psi7 gives divergent values for squared, so we can quite physical. You also shown that it's Fourier transform. This falls off very slowly for large k. Continuity, finiteness, and large k behavior of this. Consider the smooth function. Oh, great. Sketch this for various values of b to convince yourself that approximates x7 when b goes to 0. Argue for b much less than a and is roughly independent of b. Compute n when b is great goes to 0. So I think the idea here is that this is also a version of our step function. Now my familiarity with hyperbolic tangents is low, so minus 10 h. Let's look at the hyperbolic tangent in Wolfram alpha. So tan h, let's just remind ourselves what tan h looks like. Looks like this. And this is, where does it go asymptotic here? What is sine? Find sine h. I just want to find the actual form of this function. How do we calculate the hyperbolic trigonometric functions? go Wikipedia. In mathematics, hyperbolic functions are analogs of ordinary trigonometric or circular functions. Hyperbolic sine, cosine, tangent, cosecant, secant. Just as the points cos h form the right half of the equilateral hyperbola. Take a real argument called a hyperbolic angle, twice the area of the hyperbolic sector. So they're x squared minus y squared equals 1. They're the solutions to those. Okay. Go back to tan h. I just want to know what the behavior is going to be. So let's just leave this open. I might need to have some trigonometry here. Oh, that's the solutions. All right. Sketch this for various angles of B. So we know this is sine h over cosine h, the same way it is for no. So when B is 0, what are we going to get here? These go to infinity, right? As B approaches 0. Compute n when B goes to 0. So just intuitively, we're subtracting two that have different central points. So the idea being that we're doing something like this, and B must be controlling this width. I mean, that's what the intuition is, but how do we show this? You know what? I think this is probably a good point to leave it for right now. I'm going to just take a little shift off here. So where did we get today? Well, I got to nearly the end of problem set 2. We're moving quite a bit slower than I would have hoped. Pretty much all the questions, I'm having to check the answers to go back before I'm going first. It looks like most of the weaknesses are from earlier things. So not so much 804 content, but 801, 802, 803, 1801, 1802, 1803. In particular, there's some calculus stuff. There's some Fourier transform stuff that some of the math I'm still fuzzy on. So overall, this is looking like there's quite a bit of stuff to learn. I don't know exactly how I want to proceed right now. I think probably what I'm going to do is Starting tomorrow, I'll try to finish question 8, move on to problem set 3, 4. If it's looking like 3 and 4 are the same story as problem set problem sets 1 and 2, meaning that there's a lot of questions that I'm not getting, I don't know whether I want to push through all the problem sets without fixing some of these weaknesses. Now, this is a kind of a trade-off. If you have fewer weaknesses, so you kind of generally understand that there's just some minor tweaks, I generally prefer to cover as much as possible, because then you can have better breadth and figure out where to allocate your time. However, the problem is that a lot of these things are cumulative. So if you have a lot of weaknesses, it makes it even harder to do stuff further out. So you end up pulling back and working on fixing some of those problems first before you go further. So what are some of my problems? Well, I think I would, let me just bring this up so I can describe it, because I'm going to do a little analysis at the end of the day. Let me, just going to open this page here. I've given myself enough space to finish that section. So let's just call this day 4 review analysis. So what are some of my weaknesses? Well, number 1, I would say there are some conceptual holes. Overall, I would say these are not too bad, but let's look at, some of them are definitely 803 holes that need to be filled. Like, these are big problems here, that they're large subjects that I haven't covered. Some of these are older subjects. Now, the best way to fill these holes is to do Feynman techniques. This is something that that was my most popular YouTube video ever, was introducing the Feynman technique. And this was something that I've been using, all the time doing MIT Challenge, would use the Feynman technique. And it's really good for plugging conceptual holes where you don't quite get something. And I find going through it meticulously, really trying to explain it myself, is helpful. Now, there's quite a few conceptual holes, so I'm going to work on those. The second I'm going to call technical holes. I'm just going to call them technical holes right now. I don't have a better name, but basically what I mean is areas where I'm lacking in practice. So in these cases, once I see the solution, it seems pretty obvious, but it's just applying it in the moment. And so this is more of a solution procedure. You can also use Feynman technique for this. There's another way of going about it. You can use the Feynman technique, but the other way, so I'll just say Feynman in some cases. But in the other case, it's just going to be more practice. So for a lot of weaknesses I'm having because I'm rusty, let's say, so I know how to do, take a definite integral, but I haven't done it in a while. So I'm making little mistakes. Like, for instance, I was taking the integral of x squared, and I put a factor of 1/2 instead of 1/3 because I'm not thinking properly, right? Or I'm trying to do, an integral of, what was the one I was doing where I had the sign come out at the end? Yeah, I'm doing a definite integral of a complex exponential, and I'm, dropping i's, or I'm doing things like that. And these are, I think, more practice is the key. So I'm just going to keep working on stuff. If it looks like there's a specific area where there's weaknesses, I might go beyond this and work on problem sets, either from previous classes, Khan Academy, these kind of resources, to build some of those holes. I might play around with them a little bit more, get a little bit more practice with them. Just do some practice integrals, do some practice, work with some of the complex functions. Some of them can also be fixed up with conceptual things, because if you have a good conceptual picture, you can just look at what you're doing and be like, whoa, that's not right. Now, I have been doing that, but I mean, accuracy and computation and calculation is important. So there's a mix of both. Now, there's a lot of holes right now. Like normally I would say when I was doing the MIT challenge, few classes were this difficult for me. Most of the time I was doing them, I was, I have some holes, but I'm getting good chunks of the stuff right. This would be, I would say, on the harder end for classes I took. There were classes that were this difficult that I took, but they usually took me longer. So this is going to be on that order of difficulty. And part of that is, again, missing the prerequisite. Part of it, I think, is just that the expectations for doing integrals, for doing calculus, for doing basic physics is just much higher. It's just expected that you should have it like this. And for me, it's definitely not like that. So what am I going to do? Well, let's see what the plan of action is. I think the plan right now should be finish. So let's finish P set number 2 at the very least. Let's finish that. Let's go through 3, maybe up to 5. The one thing is that these are largely covering different things. So, I mean, there's going to be some cumulative weaknesses, but I seem to think that my problems are different in each. So we're going to go through that. That's probably going to take us, at the very least, if I go all the way to 5, that's definitely going to take us till Friday, maybe also Monday. I basically been doing it's taking me about 5 or 6 hours to do each problem set. I mean, they're long problem sets, so it might take me a little bit longer. So we'll see how long that takes. And then after, I'm going to say we're going to start doing some Feynman and other practice to fill these holes. I don't really want to move on past lecture 10 with this many holes right now. I mean, some of the holes, the technical holes right here, I think these holes are just going to be filled with more practice, and that's going to keep coming. But definitely the conceptual holes I want to fill. And I think the conceptual holes that underpin some of the ideas I need to be fluent with, that I kind of remember, but I'm not as fluent with, I need to get a refresher on. So do I want to go through this and work through these Feynman techniques beforehand? I think I do. And so let's leave it right now. I've been doing this again. This is 3 hours and 20 minutes right now for this session. I think that that's probably all I can reasonably put in, and I have plans in the evening, so I won't be able to keep studying after this point. But let's pick it up tomorrow morning and see where we can go from there. I'll just quickly check over to see if there's any questions that I mixed. So we have some questions. Let's see. I think that's good. Oh, what is your pre-work preparation and your post-work desensitization? You try to fully render everything, you just learn and connect everything you need to already know. Like per session, I think you can just see what I'm doing right here with the plan. So my time scale for getting this understanding is obviously not in one session. There's too many concepts, too much stuff we're doing. I try to understand stuff immediately when I can, but it's clear that there's some stubborn points that are going to require digging deeper, that are going to require care and attention that I'm not maybe giving them right now. So this is sort of my process. You have to think of it over longer time scales, because there's a lot of details, lots of different concepts, lots of things at play here. And so you have to kind of build it up over time. So I think this is good. I'm going to leave it for right now. Thank you to everyone who's been watching it so far. It's been kind of interesting doing this live on camera. I hope that you can appreciate that I don't pick these projects just because I'm going to ace them right away, because you can see I'm struggling right now. But I'm hoping that this struggle is going to be replaced with some knowledge. I don't think that over a month I'm going to become perfect in any of these things, but I definitely would like to get to a point where I can at least answer the kinds of typical questions I'll face, even if that is a little bit from having memorized some solutions or memorized some patterns that I need to use, as well as having some deep conceptual intuition of these core ideas in quantum mechanics. So obviously learning is a lifelong endeavor. I don't think that perfection is possible. It's not going to be possible, at least in this month-long period of time. But let's see how far we can go. We've only done 4 days so far. So I think if we keep working at it, we can get pretty far after a month. All right. See you.